Hi everyone. So today we're going to continue on 3.5, basis and coordinates. So the last one we did was to talk about theorem 3.5.3, which stated that if you have a vector space and with a known basis, we can actually rewrite all the elements within that vector space using a coordinate vector. And that coordinate vector, that change from the object in the vector space to the coordinate vector is a linear correspondent. Basically meaning you can view of it as a linear operator that operate on the object in the vector space, and the output of the operator would be a vector in Rn. Now, I do want to kind of show you example of this. So let's see. So show you a very simple example. So imagine in R3, okay, let's say we're given a position vector. So just use this example to kind of show you how basis work. So you probably remember seeing something similar in last year in multivariable calculus. So suppose I have this vector right here, which is 2, 3, 5. So let's say you probably remember this problems from last year. So let's say I want you to find the coordinate vector of vector x with the standard basis. So if you probably remember, the standard basis in this case is E1, E2, and E3. And so you probably remember, hopefully remember from last year, one of the advantages of a standard basis is that the standard basis, when applied to a position vector, basically give you the standard basis, basically give you the position vector as the coordinate vector. It is the only basis that we know where the position vector is actually equal to coordinate vector. Any other coordinate vector, any other basis would not do that. So in this case, basically means the following: if I have vector x, which is equal to 2, 3, 5. Technically speaking, it's just 2 times the vector 1, 0, 0, plus 3 times the vector 0, 1, 0, plus 5 times the vector 0, 0, 1. And 1, 0, 0 is vector E1. 0, 1, 0 is vector E2. And 0, 0, 1 is vector E3. Oops. So therefore, basically give you this coordinate vector 2, 3, 5. And as I said, the coordinate vector in this case is exactly the same as the position vector because that is the advantage of using standard basis. As a matter of fact, for the most part, we will be using standard basis because it's just easy to deal with. Now, but of course, if we change the basis, then it would definitely change the coordinate vector. While the position vector remained the same, it indicates the same exact position, the coordinate vector would now be different because the basis is different. In other words, meaning that it's basically require different steps, different ways to get to the same position. So in here, let's say I have the basis that I'm going to ask you to use is these three vectors. 1, 0, 0, 1, 1, 0, and 1, 1, 1. Notice that these three vectors are definitely linear independent because they are not multiple of each other, and it is impossible for you to add any two of these vectors in any linear combination form to get the remaining third one. Okay, if you think about it, it makes sense because there's no way for you to add 1, 0, 0 and 1, 1, 0 to get 1, 1, 1 because the last number is 0. There's also no way to add 1, 1, 0, and 1, 1, 1 to get 1, 0, 0, because no matter how you add the last number, when you add the second and the third vector together, we'll always get a 1, which cannot be the first vector because first vector always have a 0 in the third numbers. Okay? And then similarly, you cannot add the first and the second one to get the first and the third one to get the middle one because of the same exact reason. So therefore, these three vectors are definitely linear independent. And you can try as hard as you can. There's no way for you to add any two of them to make up in any way with any coefficient to make the third one. With that being said, now how do you form the coordinate vector? So if you remember how to do that, I would strongly recommend that you go ahead and pause the video and give it a try. But if you don't remember, then I'm just going to go ahead and continue and show you the answer. Okay? So basically we're saying that vector x is going to equal to some coefficient times 1, 0, 0 plus some coefficient times 1, 1, 0 plus some other coefficient times 1, 1, 1. So remember, this is nothing more than just forming a system of linear system of equation. So vector x will be in this case 2, 3, 5, and therefore equal to a 0, 0 plus b, b, 0 plus c, c, c. And if I combine the right side together, I basically have this set of system of equation. 2 equal to a plus b plus c. 3 equal to 0 plus b plus c. And then 5 is equal to 0 plus c. So therefore, it automatically tells me that c is 5. So that's nice. And what happened to b? Well, b must equal to -2. And then a must equal to -1. So therefore, combining this tell me that the vector x is equal to -1 times 1, 0, 0 plus -2 times 1, 1, 0 plus 5 times 1, 1, 1. So therefore, it tells me that the coordinate vector will be -1, -2, 5. So that becomes the coordinate vector. Notice that the coordinate vector is different than part A because of the basis being different, which is the reason why when you define a coordinate vector, you really have to define what the basis is. So in this case, I can say that this is with the basis 1, 0, 0, 1, 1, 0, and 1, 1, 1. Now, let's look at another example that's hopefully showed you why we are talking about basis and coordinates. Imagine the following. Imagine the vector space P2. And let's say we're given an element in P2, a polynomial function. P of x, which is equal to 2 plus 3x plus 5x squared. So number one, part A, I'm going to ask you to find the coordinates vectors for P of x with this basis, 1x x squared. And so if you think about it, it should hopefully give you a little deja vu when you do this. So then P of x is just equal to 2 plus 3x plus 5x squared. So technically speaking, it's just 2 times 1 plus 3 times x plus 5 times x squared. So therefore, basically tell me that the coordinate vector is 2, 3, 5. That is the coordinate vector. Notice that using this basis right here, you basically just have the coefficient define the polynomial. And yes, you're probably thinking, doesn't that look exactly the same as what we just did with R3? And yes, you are correct. Remember, P2 is very similar to R3. And in this case, the basis 1xx squared can be referred to as the standard basis for P2. Okay? Now, hopefully this would give you a little more, even more deja vu when you do it. What if I ask you for the following? What if I ask you to find the, oh, I'm sorry. Now I see what I wrote incorrectly. That's not coefficient vector. I mean coordinate vector. But then, of course, in my mind, I'm thinking like, oh, you just basically take out the coordinates. The coefficient. That's why I wrote that. But okay, let's now that corrected. Now let's go back. Find the coordinate vector for p of x, but this time with a different basis. How about the basis here? And so now, of course, the basis now is not the same as the quote-unquote standard basis for P2, and therefore it's not just going to be the coefficient. Now, but hopefully some of you notice what's going on here and recognize what we're doing. So if you do, you probably already know the answer, but if not, let's go through the process. So therefore, what we have here is this, is P of x is equal to 2 plus 3x plus 5x squared. And that is basically equal to some coefficient times 1 plus some other coefficient times 1 plus x and plus some other coefficient times 1 plus x squared. So if you didn't see the similarity between the last problem, let's continue. So therefore on this side I will have a plus b plus bx plus c plus cx plus cx squared. And that's equal to 2 plus 3x plus 5x squared. And now I'm going to collect all the like terms together. Notice that a, b, and c are all constant with no x attached. And b and c have both x in it. Bx and cx both have an x, so I'm going to factor an x. And then we just have one term to have x squared, cx squared. And that's equal to 2 plus 3x plus 5x squared. And now, notice that a plus b plus c is the constant term, therefore must equal the constant term on the other side. B plus c is the coefficient for x term, which have to equal the coefficient on the other side. And then c must equal to the coefficient of x squared on the other side. Notice that's the same exact system that we solved right here. See, the entire process mirrored the exact same thing we did. Okay, and that's the important part of why we developed this concept, is because now I can actually use the same exact idea that we used to deal with R3 in P2. Even though we talk about completely different things. This is a polynomial, it's not a position. But yet, it's kind of like a position in R3, which is one of the main reasons why we define them to be called vector spaces. Okay, because they function like a space. And therefore, we already know the answer to this. A is -1, B is -2, and C is 5. So therefore, tell me that vector x, which is equal to 2 plus 3x plus 5x squared, is the same as -1 times 1 plus -2 times 1 plus x plus 5 times 1 plus x squared. And therefore, we now have a coefficient, coordinate vector right here with the basis 1 plus x, 1 plus x squared. So hopefully this example kind of illustrates to you why we're doing this. Because now I can actually use all this coordinate vector to describe object in a vector space as long as we have a basis for it. And of course, remember the important part here is to identify the basis correctly, because remember your coordinate vector is relative to a base. So therefore, you cannot not define the base, but just give the coordinate vector. And of course, in most vector spaces, there is some kind of standard basis that you can use to describe the object. Okay, like in this case in P2, this is the standard basis. Now, show you another simple idea. Okay, let's say in P2, with the basis, let's just use the standard basis just to make it things easier. Let's say we're given two polynomial function in this case, well, which I can call them vectors in the vector space P2, but let's just call them a polynomial function. So let's say we have these two polynomial functions. Okay. Let's say I'm going to ask you to find the function s of x, which is equal to p of x plus q of x. Very simple. So, I mean, you can definitely do that. I mean, you learn how to combine polynomials together. So one way to do that is to do this way. Is to simply just do what you were told. So s of x is equal to p of x plus q of x. And therefore, it becomes 2 plus 3x plus 5x squared plus negative 1, plus 4x minus 2x squared. So you basically combine like terms. So 2 minus 1 is 1, 3 plus 4, 3x plus 4 is 7x, and then 5x squared minus 2x squared is plus 3x squared. So that's my answer, plain and simple. But of course, you can also think of it this way instead, which is technically what some of you probably thinking about doing anyway, is to think of them as coordinate. So p of x is equal to 2 plus 3x plus 5x squared, which basically tell me that is the coordinate 2, 3, 5. Q of x in the standard basis, which is negative 1 plus 4x plus, minus 2x squared. In the standard basis, that just gives the coordinate vector negative 1, 4, negative 2. So now if I think about s of x, which is equal to p of x plus q of x, I can think of it as adding these two coordinate vectors together to form, and this is now the coordinate vector for s of x. And so now I can then say, well, s of x would just be equal to 1 plus 7 times x, which is 7x, plus 3x squared. So notice that I can actually just, in this case, because we have a function and we have a basis for this vector space, I can actually just think of it in terms of just pure numbers and actually just work with numbers instead of working with the polynomial function and provide the same exact answer. So that's actually very powerful. When we do that, we can then allow us to not worry too much about what the object is, but just focus on the vector and the list of numbers. Now, just one more thing I want to talk to you about in this video. So, because the next thing I want to talk about is really long, so I don't think I can fit into this video, and I also don't want to split it in the middle. So, just one more thing I want to talk to you about this concept here of basis. Notice that if I have a basis for a vector space, I can actually define it using coordinate because the vector space is spanned by the basis. Now, more interesting is that the fact that when we solve differential equation, the solution doesn't necessarily form the entire vector space, but usually forms some kind of subspace within a larger vector space. So therefore, if I can also define a subspace using this concept of basis, then I can do exactly the same thing we just did, just in a smaller scale with a smaller vector space. So you probably remember learning this. One of the easiest way to actually define a subspace is by defining it using span. So therefore, imagine the following. One of the easiest way to define a subspace within a vector space is to provide a basis, or technically the span, for the subspace. So therefore, if you simply define some function as the basis for the subspace, then you can actually generate the entire subspace by defining the linear combination. So how does that work? Well, let's show you. So let's say consider the vector space. Consider the continuous function vector space that go from negative infinity to positive infinity. We can now define a subspace by the following. Remember, whenever you define a span, the span would automatically create a subspace within the vector space that you choose the vector from. And here I just have to make sure that whatever I choose, they have to be linearly independent so they will form a basis. So technically speaking, if you recall learning in 3.2, we talk about using span to define subspace. We are basically doing the exact same thing, only the exception here is that instead of using a span, we use a basis. And the only difference between a span and a basis is that a span doesn't have to be linearly independent. A basis must be linearly independent. That's all that is. So in here, I just don't make sure that what I'm choosing to form the span would be linearly independent elements. So how about we do this? We can define a subspace of z negative infinity to positive infinity with the span of, let's say, these two functions, e to x and e to negative x. These two functions are definitely linearly independent because I cannot multiply one of them to get the other one. Okay? And of course, in here, meaning scalar multiple. So neither of these two functions are scalar multiple of each other because one is e to x and one is e to negative x. So I cannot multiply one of them by a constant, then make it into the second one. And remember, when I multiply a constant, I cannot multiply into the exponent. That's the reason why. And it has to be multiplied by a constant, not a variable. So in this case, what this subspace would be. So if I define this subspace as the span of these two vectors, I can go and say this. It basically equal to any function in this form. That would be the type of functions. And in this case, we know that the dimension, let's say we define this subspace, I'm going to give it a name, I'm going to call it subspace V. And we know that the dimension of V would have to be 2 because it has 2 elements within this vector space. Now, it shouldn't be too hard to see that it has to form a subspace. Why? Because of the following. Let's just quickly go over the proof. So, does it contain the 0 vectors? Well, z of x would equal to 0, which is just basically equal to 0 e to x plus 0 e to negative x. Essentially, it corresponding to the coordinate vector 0. That's the basic idea. The 0 element in this case is the 0 function, which corresponding to the coordinate 0 vector, which is 0, 0 in this case. Okay. Additive closure. addition closure. Suppose I have function f of x, which is equal to a1 e to x plus b1 e to negative x, and a function g of x, which is equal to a2 e to x plus b2 e to the negative x. Then when I combine them together and form f plus g of x, that just equal to a1 plus a2 e to the x plus b1 plus b2 e to negative x. Simple as that when I add them together. So notice that in here, once again, what the idea is that f is equivalent to the vector a1, b1. G is equivalent to the vector a2, b2. And therefore, f plus g would be equivalent to the vector a1 plus a2, b1 plus b2. There you go. So once again, with the basis defined e to x e to negative x, I can just simply focus on the coefficient, which in this case form the coordinate vector that I'm working with. We can definitely also do the scalar closure, which should be pretty straightforward also. So let's say f of x is equal to, I don't know, a e to the x plus b e to the negative x, since I don't need the subscript anymore, I only have one. And so what happens if you take r times f of x? Well, that just equal to ra e to the x plus rb e to negative x. So once again, the idea is that f would have the vector AB, then RF would have the vector RA and RB. There you go. The coordinate vector work out exactly the same way as you dealing with the function itself. But of course, the idea here is that if you use the coordinate vector, then you do need to know the basis to actually form the correct element. In this case, form the correct continuous function. All right, at this point, I think I'm going to stop this video at 27 minutes, which is good. Tomorrow, the next video will talk about very important theorems. Quite confusing. We're probably going to spend the entire video talk about it. All right, I'll talk to you guys later. Okay, bye-bye.